Okay, so we're going to record, and we have systems of differential equations. And in the new book, it's chapter 9. And we already discussed that one way you can solve a system of differential equations is by using the diagonalization technique. And so this is, you'll see some very strong similarities to that. But I wanted to point out some notation here. And again, it depends on a little bit what discipline you end up in as to how they go about writing these things. So let's point out sort of the math way to look at it. So these systems of differential equations are often written in the form, so they call it like the matrix form. So you have this x matrix, or this x vector, not matrix, this x vector, where you're taking the derivative of t as the variable is equal to a of t, so the matrix A times a vector x of t plus this coefficient constants. So you have this ax plus b form, but it's with the derivative, so that way you have a differential equation. So for example, if I had x1 of t equals 3x1 plus 2x2 plus the cosine of t. So that's x1, take its derivative, equal 3x plus 2x2 plus cosine of t. And then the second equation was x2, take its derivative, and that's equal to 4x1 plus x2 plus x times e to the t. That is a system of differential equations, and the way we could write that in matrix form would be this ax plus b form. So in this case, we'd have x, the derivative, that vector, take its derivative, and then our A matrix would be 3, 2, 4, 1. And then we'd have x1, x2, and then plus the cosine of t and x times e to the t. This would be our matrix form. Let's see. Here's another example. Let's say we had the second derivative of the function x with respect to t minus 4y equals e to the t. So now we have x and y instead of x1 and x2. I'm going to make my x a little nicer. So now we're talking about the second derivative, and then we also have the second derivative of y with respect to t plus t squared times dx dt. And that was equal to sine of t. So this is a system of differential equations with x and y, but now we have the second derivative of each. And so there is a very, very, very powerful technique that we sort of should get comfortable with. It takes a little practice. We've done it before, but let's do it again. So just looking at x, I'm going to make x1 equal to x. So I'm just taking this and making x1 equal to my x variable. Then if I take the derivative of x1, that's equal to the derivative of x, and I'll make that equal to x2. Then if I take the second derivative of x1, that would be the same as the second derivative of x, which would be the first derivative of x2. Then I'm going to continue on. I've written that kind of goofy because it was messy. Let me try and make it look a little nicer. This is the first derivative of x2. So I have x1 take the second derivative. That would be the same as taking the second derivative of x. And then that's equal to the first derivative of x2. Then I'm going to continue on. I'm going to make x3 equal to y. So I'm doing y. What's next on the list is x3. And then I do the same idea. I take the first derivative of x3, and that's equal to the first derivative of y, and I'll call that x4. Then I take the second derivative of x3, and that's equal to the first derivative of x4, which of course is, we can just leave it there because that's all we need, right? We don't need to write the next one down. We don't need an x5, right? Because we could write x5, but it would be a waste. So what I've done is I have made this substitution. So I've converted this x2, the x second derivative, I should say, not x2, and this y second derivative into a system of equations of x1, x2, x3, and x4. So let me write this. I'm just going to start with the one on the top up here. I'm going to start with this one. So x2, take its derivative, is equal to, and then I move this to the other side of the equal sign. So that's equal to plus 4x3 plus e to the t. So x3 is the same as y. x3 is the same as y. And the second derivative of x, the second derivative of x is the same as the first derivative of x2. And continuing on, I'm going to go down below and now do this one. So I sort of write them out of order. You have x4 take the first derivative, and that's equal to minus t squared times x2 plus sine of t. So I took this term, moved it over to the other side, so it's minus, and then t squared, and then the first derivative of x is x2. The first derivative of x is x2. And now that I've done both of my systems of equations that were written originally, I do x1, take the first derivative, that's equal to x2, and x3, take the first derivative, and that's equal to x4. So I mentioned that I sort of write them out of order because we normally would start with x1 at the top, and then x2 and x3 and x4, but I wrote them in terms of the way that they showed up here in my system, and then once I do that, I just fill in the gaps. So then if I put that all in order, I would have x1, take the first derivative, is equal to x squared or sorry, x2, not x squared. And then x2, take the first derivative, is 4x3 plus e to the t. And then x3, take its derivative, is equal to x4. And then x4, take its derivative, is equal to minus tx2 minus t squared x2, and then plus sine of t. So I've sort of written it out as a system in order, sort of spaced out. And then I just make a matrix in that form. So I write my system as the x vector, take the derivative, is equal to, so then I'll have 0, 1, 0, 0. Make those a little closer. 0, 1, 0, 0. And then 0, 0, 4, 0. And I'll have 0, 0, 0, 1. And then a row of zeros. And I'm going to multiply that by x1, x2, x3, x4. And then plus e to the t, 0, 0, and minus t squared. Is there a squared there? There's a squared. X2 plus sine of t. I could write it that way. And so what I've done is converted this, this system of differential equations that was a higher order into a first order system of differential equations. And that is an important idea. And you know, you practice that about 200 times and it becomes a lot easier to do, of course. So let's practice one more time. How about for example, if we had the second derivative of y.
Wait, I have a question.
Yeah, go ahead.
About the one that we just did. Why wouldn't we put negative t squared in the x2 column in the A matrix, like under the one? In the...
Put it right here?
Yeah.
So if you put it there and multiplied out that last row, that would be fine. There would be nothing wrong with that.
Okay.
I just decided to put everything with a t over to the right-hand side.
Okay.
And that's only for the purpose of helping us solve this AX matrix part.
Okay, yeah.
So if you put the t here, then you wouldn't put it over there.
Right.
But then this would have a variable in it.
Right.
And the technique of finding the eigenvalues and eigenvectors would be harder to do.
Yeah. Okay.
That's a good question. All right. Anyone else? No? Good. Okay. So how about this one? The second derivative of y with respect to t plus 4e to the t times dy dt. So the first derivative of y with respect to t minus 9 t squared times y equals 7t squared. So we could write this y second derivative plus 4e to the t y first derivative minus 9t squared times y equals 7t squared. We could write it that way. Those are equivalent forms with different notation. So what I'm going to do then is write this as a system. So I convert this second order differential equation into a system of differential equations. So I get x1 equals y. Then I take x1 and take its derivative. So that means y gets a derivative. And I make that equal to x2. Then I take the second derivative of y1, which is the second derivative of y2. And so that's the first derivative of x2. And then I stop. Now, sometimes what happens is I keep going, right? And I do the third derivative and the fourth derivative, and I realize, oh, wait, I don't need that. So I know where to stop because this is the second derivative of y, second derivative of y. Once I've gotten that down, then I know I'm done. I don't need to go anymore. But if you go too many, it's okay. You just won't use those for anything. So then I'm going to convert this. I'm going to convert this. So I have y double prime, which is the same as x2 first derivative, plus 4e to the t times y prime, but y prime is x2, minus 9t squared times y, but y is x1, and that's equal to 7t squared. Then I have this x1, I have x2 with the derivative, x2, and then I have an x1. So I need another equation, right? So then I do x1, take its derivative, is equal to x2. And this is a system of differential equations. So I've converted a second order system of differential equation, or a second order differential equation into a system of differential equations, all of the first order. And so when I write out my matrix form, this would be, let's see, this would be 0, 1, 0, 0 times x1, x2. So if I put this on the top, I'd have 0 and then 1. That's this coefficient of 1. And then I'd have all the rest of these terms have t's. So this would be 0. And then I would do plus 0 on the top. And then 7t squared plus 9t squared times x1 minus 4e to the t times x2. So I took this and then I put all of these terms on the other side of that equal sign. And that's where I get the positive and negative with these. So what I've done is converted from the second order differential equation into a system of first orders. And the real reason I would want to do that is because we have techniques to solve systems of differential equations. And then also, this is really a big one. So MATLAB and other algorithms are out there that know how to deal with so Runge-Kutta for systems. Now, that is actually beyond the scope of this class, but it certainly would be something you might encounter when you have a system of differential equations. MATLAB has the ability to do that as a built-in command for systems, or there certainly is code algorithms that you could write. Okay, so that's the real reason that we want to talk about those techniques, is because we can convert this really brutally ugly differential equation into something that we can solve it numerically using a system solution solver. Okay, let's talk about section 9.4. So this is the case for when our b of x is equal to 0. Let me double check that I have the right section. Yeah, 9.4. So we would have then x of t equals ax no ax, just a times x of t. And before, remember, we had this plus b over here, but this is 0 now, right? So it's just our derivative of t equals a times x. And so when b is equal to 0, so often it's just given to us as, it'll say, solve the system of differential equations with a equals 0, 2, minus 3, minus 2, 4, minus 3, minus 2, 2, minus 1, for example. So often it's just given to us as the A matrix, and it's understood that we plug this A matrix into this, this system form. So what happens is there's some cases that we run into that we need to sort of think about and worry about. And the first case is case 1. If our A matrix is non-defective. So our A matrix is non-defective. So remember, non-defective means there is a complete set of eigenvalues and eigenvectors. So the case 1, if we have non-defective matrix A and we have real roots. So our eigenvalues are real. So let's do that example that we just did. So for example, if A, take its derivative or vector equals AX, and A equals the one I just wrote down, 0, 2, minus 3, minus 2, 4, minus 3, minus 2, 2, minus 1. So, by the way, we already know how to solve this. We could solve this using the SA S equals D form that we did before. The inverse of S times AS equals D. We could solve it that way, right? We already know how to do this, but this is another sort of a view of this. This is actually easier, in my opinion. So we find the eigenvalues and the eigenvectors. So you take the determinant. So step 1 is find eigenvalues and vectors. So you take the determinant of A minus lambda I and set that equal to 0. So I've already worked that out, and we'd have lambda plus 1 times lambda minus 2 squared with a negative out front, and that's equal to 0. So that you take the determinant of A minus lambda I, set it equal to 0. In this case, it's minus times lambda plus 1 times the quantity lambda minus 2. So then lambda 1 equals minus 1, and lambda 2 equals 2 with a multiplicity of 2. So for lambda 1 equals minus 1, we would plug that back in and find the eigenvector, and I found that to be V1 equals 1, 1, 1. And then for lambda 2, which is equal to 2, I plug that back into A minus lambda I, do the reduced row echelon. I got V equals R times 1, 1, 0 plus an S times minus 3, 0, 2. So I got two linearly independent vectors there. And so I'm going to call V1 or V2 equal to 1, 1, 0 will work. And V3 equal to minus 3, 0, 2. So I have my 3 eigenvalues, minus 1 and 2 repeated twice. Then I found the corresponding V1, V2, and V3 that are eigenvectors. And so what I do, very simply, my solution as an x vector is equal to, I put in V1, V2, and V3 as columns in a matrix, and I multiply that by C1 times e to the lambda 1 times t, and then C2 e to the lambda 2 times t, and C3 e to the lambda 3 times t. And so in our specific example, that would be x is equal to the column vector 1, 1, 1, 1, 1, 0, minus 3, 0, 2. And I would multiply that by C1, e to the lambda 1 was minus 1, so minus t. C2 would be e to the 2t. And then C3 would be e to the 2t. And that would be it. Now, some people will write this a little bit different. This is a solution. Nothing wrong with this solution. Some people would write it out a little bit differently. So let me put also. You could write it out as x1 of x equals, this is the way I was taught to do it, e to the lambda t times v1, and x2, no idea why I put an x there. This is a t. And x2 would be e to the lambda 2 t times v2, and so forth. So that would be the other way to do it. So this would be xn of t equals e to the lambda nt times vn. And so in our case, I would just write that as x1 equals e to the minus t times 1, 1, 1, and x2 equals e to the 2t times 1, 1, 0, and x3 would equal e to the 2t times minus 3, 0, 2. So you would write that out, and then you would make another line that looks like this. You'd go x of t equals, and then you put c1 times x1 plus c2 times x2 plus c3 times x3. Each of these needs a vector on the top too as well. And then that would be your solution. So either of those two is fine. Also, some people will write it out, the whole thing, and there's nothing wrong with that. So they'll write x of t equals c1 times e minus t times 1, 1, 1 plus c2 times e to the 2t times 1, 1, 0. And by the way, any of these methods is perfectly fine. Just trying to expose you to different ways that people write these. Minus 3, 0, 2. So this would also be fine. Any of these ways I think is perfectly fine. So our book often writes it in this form as like this matrix times the C1 e to the lambda t. I think a lot of other books will write it this way and then put this form down there where you put the C1, C2, C3 in front. That's fairly common as well, as long as you make it clear what the X1, X2, and X3 are. And then other books, especially some of your, like graduate level math books, will write it in this form with the blue, which is more descriptive, right? It's just putting everything together nicely. If I didn't write so sloppy, it might be better. I haven't quite managed writing on the tablet. Okay, very, very exciting. So the next thing we have is what happens if we have case number 2, where the matrix is non-defective and it has complex roots. So This is case 2. So this is matrix is non-defective with complex roots. So, I am just going to do the situation where you have a 2 by 2 matrix. You could also have a 3 by 3 matrix, and or 4 by 4 or something bigger. But I'm just going to do a 2 by 2 example, and then leave the rest for, you know, another class or a class that you have a situation where you actually encounter that. I just want to give you a flavor for what we're doing. And again, that's because the time has run out in the semester. You can read through this section in your book as well if you were interested to learn more about it. But again, we've run out of time, and so we can't spend a lot more time dealing with this. But you know, this is 9.4. You could read more about it in the section 9.4. But I'm just going to do this the simplest case with a 2 by 2 situation. So, for example, I have x derivative equals a times x, and I have an A matrix equal to -1 minus 2, 2 minus 1. And the determinant of A minus lambda I equals lambda squared plus 2 lambda plus 5 equals 0. So the determinant of A minus lambda I, when I set it equal to 0, is lambda squared plus 2 lambda plus 5 equals 0. So I end up with lambda equaling -1 plus or minus 2i. So this is this complex root. And if we talk about this with our a and b, our a equals -1 and our b equals 2. So this is a plus bi form. This a equals plus or minus bi. And so there's some theory that's going to go on here, but I'm gonna skip over, and I'll let you read about it. I just want you to see the form. So we can put this in x1 of t equals e to the at times cosine bt sine of bt, and then x2 of t equals e to the at times minus sine bt, and then cosine bt. So in the case of 2 by 2, so this is the case of 2 by 2. And we find complex eigenvalues. We make an x1, which is e to the at times the cosine of bt, sine of bt, and x2 is e to the at minus sine of bt, cosine of bt. And then we write out our solution as like this. X of t equals c1 times x1 of t plus c2 times x2 of t. And if we put these together, you'd have e to the at times, that would be c1 cosine bt minus c2 sine of bt, and c1 times the sine of bt plus c2 times the cosine of bt. So all I've done is combine these two together with addition, and I've just written it like this. So again, the way I learned it when I was taking this class was to write it in this form, but there would also be nothing wrong with writing it like this as long as you had said what x1 and x2 were. And so for our particular example, where we had up above, -1, -2, I apologize. I think I made a typo. On that. I think this matrix needs, I forgot to write it. I think this matrix up here needs a minus. I apologize about that. I forgot to write it when I was going through. So please fix that. And then, but we have our A and our B. So this would be x of t equals c1 times e to the a, which is minus, of course. So minus 1t. So e to the a t would be e to the minus t. And then we would have cosine, or c1 times the cosine of b, which was 2, t I don't need both C1s. Take this C1 out because I used the C1 already. I almost wrote two C1s, which would have been no good. C1 e to the minus t times cosine of bt is 2t minus, let me put this part first, sine of 2t, and then plus c2 e to the minus t, and the same idea with the copying this one down. So minus sine of 2t cosine of 2t. So, or we could just write them together, which is the way I learned to do it. E to the minus t times c1 cosine of 2t minus c2 sine of 2t. Again, these are all equivalent, just different flavors of writing it. And then c1 times sine of 2t plus c2 times cosine of 2t. So that's the simple case. That is the case of a 2x2. When we have a 3x3, it's slightly more challenging. And again, I'll let you sort of read that over. And I want you to get a flavor for it, because if that case comes up in another class, at least you're sort of getting an understanding of, I have these sines and cosines that I have to put together. So that's case number 2. Okay, let's take just a moment break and see how everyone is doing here. So let's share the screen again. So this is case number 3. And that's when our matrix is defective. So it's missing an a complete set of eigenvectors. What do we do? Now, I think I told you the story. I asked in grad school, I was taking an engineering course. I'd already taken differential equations, and so I knew about this case. So I asked my engineering professor, oh, what do you folks do when you have a non-defective, or when you have a defective matrix? And he paused and kind of looked at me puzzled and then said, oh, that's right. You and Ronnie are from the math department. We just don't do structures that would have defective matrices. So that's an interesting idea, but the truth of it is the case still exists where you have defective matrices. So let's talk about and get sort of a flavor of what happens here. So for example, we have the A equals 1 minus 3, 3, 7. So this matrix, when I find the eigenvalues, I get lambda equals 4. And remember that I have to do where I plug A minus lambda I times V equals 0. And I do the reduced row echelon form. So when I find that, I'll have lambda minus, so I take the determinant of A minus lambda I, set it equal to 0. And when I did that, I found that I had lambda equal to 4. So then I do this A minus lambda I, and that would be 1 minus lambda minus 3, 3, 7 minus lambda. And when I plug in the 4, I get minus 3, minus 3, 3, 3. And I do reduced row echelon form of that to get 1, 1, 0, 0. And then I solve that and I get x1 equals minus 1 times x2, and x2 equals a free variable. So that means I have this eigenvector t times minus 1, 1. And I have a 2 by 2 matrix with only one eigenvalue and one eigenvector. So this is a defective matrix. And if I wrote out the solution, I would say x1 of t equals e to the lambda t times v1, which in this case is e to the 4t times minus 1, 1. But this is defective. There's, we need another one, right? So this is trouble. So this is a problem because we need another lambda 1 we need another V is what we really need. Okay, so what we do, the idea is to build what's called chains of generalized eigenvectors. Okay, so let's do this as carefully as we can. So we already found A minus lambda I times V, we call this V1, equal the zero vector. So if we took, and I'll actually write it out, A minus lambda I was A minus lambda I equals -3, -3, 3, 3. And if we multiply that by our V1 that we found, which was -1, 1, and if we multiply those together, -3, -3, 3, 3, times -1, 1, we would indeed get 0, 0. Okay, we already found that case. That's what the eigenvector does. Remember, it maps to the null space. So here is the part that's kind of tricky to get at first, but we'll actually work it out to see if it works. So notice that if I take A minus lambda I and I square it, and I multiply that by V1, I also get 0. What does that mean? Well, A minus lambda I is -3, -3, 3, 3. And if I square that, so I multiply it by itself, I'm going to do that in my calculator. You should too if you have a chance. So I'm going to have a 2 by 2 matrix with -3, -3, 3, and 3. And I multiply it by itself, or I square it. What do I get in this particular case? Times V1. I get 0, 0, 0, 0, because that's what -3 times -3, -3, 3, 3 is 0, 0, 0, 0 when I square it. Then I'm going to multiply that by -1, 1. So obviously I'm going to have the 0 vector. So the big idea here is that A minus lambda I, when I squared it, became 0, 0, 0, 0. Okay? So I just want to point out that that's what happened, all right? So we'll use that in just a minute. For V2, our other one that we need, the second eigenvector, we need to find a V2 that's not equal to 0. So let me do it like this. A minus lambda I squared times V2 that's equal to 0, such that A minus lambda I times V2 equals V1. And then what we do is our x1 is equal to their e to the lambda t times v1. That's what we've been doing before. And our x2 is equal to e to the lambda t times v1 plus v2. And the reason we're multiplying by t is e times lambda t times v1. And if I distributed this e times lambda t times v1 without the t, they would be equal. And so therefore they would not be linearly independent. But when I multiply this t, I get this situation of linearly independence. So this is the case. This is if we lack only one eigenvector. If we lacked multiple eigenvectors, we would have to build multiple chains. And that, my friends, is not always easy. That can be extremely tedious and challenging. We'll really, for us, only look at this 2x2 case. So this that I've written here in blue is sort of the theory for the 2x2 lack one eigenvector. Okay, so let's go back to our example that we had. So back to A equals 1 minus 3, 3, 7. And remember, lambda equaled 4, and my V1 equaled minus 1, 1. Okay, so A minus 4i, because lambda was 4, squared times V2 equals 0, such that A minus 4i times V2 equals V1. And let's look at this. V2 equals 1, 0 would work. Now, I'll get to how I found that in just a second. So that would work. So if I did that, I would have A minus 4i, A minus lambda I, and squared times 1, 0. Does that indeed equal 0, 0? Well, yes, it does, because if I do A minus lambda I and square it, I get the 0 vector. So I could, as it turns out, choose any vector I wanted, as long as it wasn't a linear combination of 1 minus 1. So A minus lambda I, or in this case 4, A minus 4i squared, times 1, 0 equals the 0, 0 vector. So that's the first thing we need. And the second thing I need is for A minus 4i, A minus lambda I, times that V2, which is 1, 0 in this case, has to equal V1. So is that true? Those are the two things I need. So I have minus 3, 3, 3, and I put 1, 0 there. And when I multiply that out, I'll get minus 3, 3. And minus 3, 3 is equal to 3 times minus 1, 1. So this one worked just fine, right? So as long as it's some linear combination of that. So we're good to go. So how I would write this is x1 of t equals e to the 4t times v1, which is e to the 4t times, we could write it as minus 1, 1, or we could write it as minus 3, 3. Doesn't matter. I'm just going to leave it as minus 3, 3, as long as it was a linear combination of our v1. And then our x2 is where we have this eigenchain. So our x2 would be e to the 4t times v1 times t plus v2, which is e to the 4t times t times minus 3, 3 plus 1, 0. And so those would be the solution. So what you do then usually is write this x of t equals c1 times x1. Both of these are vectors. I forgot to put the vectors up there. Plus c2 times x2. And that's how you usually write the solution. Now some people actually write it all out where they'll put this, they'll actually write this whole thing out. But as the problems get bigger, they get bigger and bigger and bigger. So the trick here, remember, we need to find these two things we've got to find. And that is, let me write a summary. We need two things since we were defective. We need a minus lambda I when we square it times v2 is equal to the 0 vector, such that a minus lambda I times that v2 is equal to v1. So that's what we have to find. So that's for the 2 by 2 case. Okay, and in your homework, if I'm not mistaken, I have only given you a homework assignment with section 9.5. I don't think I've actually assigned any of those. That's just, this is for your enrichment, I guess, because we don't really have a lot of time to deal with this in the general case. When you get beyond a 2 by 2 case, it gets increasingly longer chains, and so you end up having to build these longer chains with longer matrices, and it takes more practice. But again, that's really for the standalone differential equations class or even a graduate level differential equations class. But I wanted to give you a flavor for that.